All right, in this video I'm going to talk a little bit about work done by a force. So the reason we're going to talk about work is because when we consider the kinetic energy change of a point particle, it changes as a result of the work. So we need to understand what that is. So we're going to start with just the formal description of work, which is the work done by a force F is F times the displacement. Now this little dot right here actually talks about a specific kind of multiplication. So we'll go into that in a little bit. The first thing I want to try to get you to understand is that this work can have different signs. It can be positive, it can be negative, or it can be zero. So let's think about an object that is moving in this direction. It has a displacement to the right. And there's a force that acts on that object, which is also to the right. In that case, the kinetic energy of this object is going to increase, right? It's going to start moving faster. And so if the change in kinetic energy is equal to the work must also be positive. It must increase the kinetic energy of this system. On the other hand, if you have a particle which is moving to the right, and you apply a force to the left, you know that this object is going to slow down. That means its kinetic energy is going to become smaller, and so the change in kinetic energy is going to be negative. And again, based on the work kinetic energy theorem, or the energy principle in its simplest form, the work done by this force must also be less than zero. It turns out that this mathematical formulation of the work done by a force as the dot product or the scalar product of these two vectors accounts for these different situations. So what is this dot product? If we're going to calculate the work done by a force, we're going to multiply vectors. For example, if I have a force that has all three components, fx, fy, fz, and we dot that, multiply that into the displacement in each direction, delta x, delta y, and delta z, that will result in the scalar product of each of the components added together. So this is how you would multiply this out in Cartesian coordinates. It's fx times delta x plus fy times delta y plus fz times delta z. So this is if you have a very sort of simple Cartesian system where you can track the displacements in each direction and multiply by each of the components of the force. Now that's usually not the case, that you have this nice simple description. Typically what you have is a situation where you have an object which is going through some displacement, and you apply a force in some direction that is at an angle to that displacement. Now if we look at this, the displacement, for example, would only be in the plus x direction, whereas the force is in the plus y direction. And also in the plus x direction, actually. So, but the point is that if we look at this situation and compare it to our calculation here, there is no displacement in the y direction. And so the only contribution that you get to the work is that which is the force in the direction of the displacement, or opposite that direction in the case of it being turned the other way. So what we can do is decompose this vector into its x component and its y component, and see that only the x component is going to contribute to a change in kinetic energy. It's going to be a positive change in kinetic energy. Therefore, this is a positive work. So that x component is f times the cosine of that angle. This leads to an alternative description of the work that some people like to use, which is that the work done is the force times the displacement, which can be thought of as f times the magnitude of f times the magnitude of the displacement times the cosine of the angle between those two. Now you can apply this cosine to either the force or the displacement. In our case, what we said was this was f times cosine of theta times the magnitude of the displacement. This cosine of theta takes on different signs, so it handles the plus and minuses. But this right here is fx in that picture right there. So this is the component of the force which is in the direction of the displacement. So the dot product, in a sense, picks out how much of that force lies in the direction of the displacement. So this work that's done can be calculated either in a Cartesian sense by multiplying the components, or by thinking about how big is the force in the direction of the displacement and multiplying those two things together. One last thing to say about this is that this is more general than working it out in Cartesian coordinates or with a coordinate system. This idea that the force picks out the direction of the displacement is actually pretty powerful. If you have something that displaces, say like that, and you have some force that points in this direction, you can still think about the decomposition of that along the direction of the displacement and perpendicular to the direction of the displacement. This actually goes back to our curving motion discussion, right? But it really stems from this idea that the only way to affect the kinetic energy is to apply a force in the direction of the displacement or opposite the direction of the displacement. So one last thing. If you have a situation where the force is perpendicular to the displacement, some of you might have already caught on to this. If these two make right angles, then the work that's done in this case is precisely 0, because there is no amount of the force that is in the direction of the displacement. They are perpendicular to each other. So this dot product of F dot delta R, when you have perpendicular components like this, is 0.